All right, what I have here is the Ninja Creami with Creamify technology. This was plugged into a power source that is far too powerful for it. Went from a 120 volts to I think a 240-volt power supply, and it failed. So we're going to take it apart and see what happened with it. The person who owns it says that they heard a pop. So chances are pretty good that this is something that broke in the board. The screws around the top here are Torx size 10. All right. So with the board out, we can clearly see where the issue is. This varistor is completely blown, which means there's most likely something else as well on the board. Oh, yeah, look at the back here. This entire thing is carbonized, and this whole trace here is completely melted. So this entire trace that comes from this pin, or at least this point here, all the way over here is completely fried. It looks like this part needs to be cleared up. We'll have to see what this is. And of course, on the other side, the varistor is destroyed. So we've got to pull this board out. This is what we have. You can see the burn trace completely removed from the board here. It looks like it's damaged here. Some carbonization. This part looks like it's also destroyed. So we're going to get under the microscope, take a closer look, and see what we can find. This varistor is a 10 millimeter in diameter, 271 volts. That is a 10 ohm resistor. These two plastic capacitors are zero point 0.1 microfarad. We'll test them. We'll see if we can test it on the board. Let's look at the other side where the real damage is. So starting here, we can see this part is completely destroyed. And that basically connects this trace here, starting from this side of the capacitor, and this large. This is one of the wires that came in originally. Coming around through here, all the way over here to this part. And yeah, this whole thing is just basically destroyed. And if you're wondering why I'm digging at it with a sharp point, the thing is if it is going to survive on the board, it would survive there. Second thing, second wire here. This looks like this trace was just completely destroyed. It's destroyed right here, coming back through to here. The first trace is a normal pathway on the board that was destroyed, but this one is a fused trace and it is meant to be destroyed. It doesn't save much money for anyone, but it does make a board almost unusable in the event of a failure. I have a couple of options here. I can either replace these burn traces with just a wire, but the problem with that is that in the event of another failure, they burn up like these did, and I don't necessarily want something that causes a fire in a kitchen appliance. So I think what I really want to do is replace them with a fuse. All I need to do is really measure the width of these traces, and I can kind of figure out the amperage needed, either to destroy this trace or destroy a fuse. However, traces are not meant to be repaired, even though I can repair them, and fuses are meant to be replaced. Just going to use some isopropyl alcohol. I have these little nano sponges that are made out of cotton. I like them. I also use a set of plastic tweezers so that I can't damage things on the board with the tweezers themselves. Just want to see, you'll notice a lot of the backing, the solder mask is coming off of these traces. This gives me a better understanding of how I can connect the fuses to the board. I need to measure how wide these traces are, and I can use that width to kind of figure out the amperage at which these traces would fail, and that will give me the size of a fuse that I can put in place. These traces look like they're somewhere between 18 and 24 mil. That is, mil means 1,000th of an inch. And these traces will handle almost 6 amps worth of power. All right, looks like I do have the appropriate varistor, 10 millimeter, 271. And we're going to use these fuses. There's a reason why trace fuses are not used in certain countries. If you're in France, they're considered to be illegal. They are designed to, what just happened here, start a fire, melt away the metal. Hopefully, it's in a place in the electronics where it won't start a fire in your kitchen. But it is not, in my mind, the safest choice. It is a choice that is kind of a jerky choice, if I can say that phrase. It seems like it's not a nice thing to do, to design something or build something that, if there is a voltage that's out of spec, is designed to catch on fire so you can throw the board away. Take that for what you will. I think one of the hardest parts is just doing some of the prep work here. Now that the first fuse is in place, that should solve the problem with the first destroyed trace on the board. This second one, this fuse trace, it's going to clean up some of the space here. Put in the same type of fuse. I've bent all the pins, bent both the legs to kind of match where they should go. Fuses don't have polarity. There's no positive or negative side. They're essentially a wire that will break if, in this case, it gets above 6.3 amps. This top leg of the fuse is, it could easily go in this hole, but this hole is, if you remember, it's where one of the wires that powers the board will come through. So I want to make certain I leave enough space. When I put that wire through, it's going to connect enough solder to the side of the fuse as well. Okay, fuses are on the board. It is not a pretty way to do things, but it is probably a lot safer than what was originally there. Um, Next thing to do is to remove this varistor. To remove the varistor, I'm just going to put my tweezers underneath just to add extra weight and maybe some extra prying ability. This is a large pad. There's a lot of copper under it. It takes a lot of the heat away from the iron and it makes it harder to melt the solder. It'll take just a bit longer for this to start melting. A little bit of flux. You'll notice that these two holes share the same pads, the same traces, so they are connected. You notice that when this melts, the thing next to it melts as well. It's just because they share the same piece of copper. All right. As I look through the board, I find it looks like it's short on the board. I see 76 ohms bridging the gap between different pads. So I'm just going to test some of the components. The capacitors I've tested so far have been good. This is a triac on the top here. This is pin 1, this is pin 2, and this is the gate. Pin 1 to pin 2. Right, try the scan. Pin 1 to pin 2. Nothing. Nothing. To the gate. Nothing. Nothing there. Went to the gate. Does have a voltage drop. In both directions. One of them is 0.03. And that's almost a dead short from diode mode. Let's see. This should be, if I look at the data sheet, from gate to pin 1, should show a low voltage reading 0.5 to 0.9. Oh, it's a lot lower than that in both directions. My tester has a hard time identifying this triac. It does show the resistances between pins, but the values it comes up with are quite a bit different from the data sheet. I'm going to order a new one of these, and when it gets in, I can compare them. But I feel like this device is definitely has a partial short and is not functioning like it should. I lost the video of pulling this off the board. This is an N-channel MOSFET. It looks very similar to the triac, but it's a different type of device. Um, this device is really the kind of the where the main power of the board goes through. MOSFETs are very, very efficient. This will take 650 volts that can run through it. I don't know if this is bad or not. I just want to pull it off and put it in the tester, see if it looks and functions like it should, and then I can either put it back on or order a new one. This MOSFET is the HF4N65, and when I put it in my tester, it seems to be just fine. So I'm going to put it back on the board. I also removed the diode, this D6 diode here. It is a GS1M diode. I have a lot of these. I just wanted to replace it because it tested a voltage drop in both directions, and in one direction it shouldn't. It should block the testing. It could be something on the board, could be the diode. I'm just gonna put a new one here, and then I'll retest it and see if it's a problem with the board or if it's functioning like it should. I'm not certain at this point. I just want to go through and test a few other components on the board. Okay, so to recap what we've just seen so far, the Ninja Creami was plugged into a 240 volt source. It is a 120 volt machine. Catastrophic failure ensued. There was a varistor on the other side of the board, a 10 diameter 271K varistor that has been replaced. It also burned up these traces. There were two of them that have now been replaced by these plastic 6.3 amp fuses. This trace that goes from this point all the way over here is most likely not supposed to fail. It's not supposed to be a fused trace. It is supposed to just be a normal cable. I could have replaced this, sorry, a normal wire. I could have replaced this with just a traditional wire. However, it did fail, and if there were another failure, it could easily set the wire arcing or catch it on fire, or it could melt. And this device goes in the kitchen of a colleague, and I don't want there to be any safety concerns. So a fuse it is. Um, and the width of the trace, I guess somewhere close to a 20 to 22 mil trace that is 22 thousandths of an inch. And if you were to look at a diagram, if you look at the typical thickness of a copper trace on a commercial board that is that thick, somewhere around 6 amps is at the point where it will have a catastrophic failure and just catch on fire or evaporate, which is what this thing did. So a 6.3 amp fuse is somewhat appropriate. It will fail like this trace did, but it will fail in a safe way where only the fuse will explode without causing a fire. Same thing with this one. This actually is where the fused trace was. It was meant to fail on this board. Uh, Not something I'm a fan of, but same thing, around the same thickness. 6.3 amp fuse is probably the safest thing I can put in place. I wrapped it around these points. This point here is where one of the wires that the power wires comes out. So I've left a gap here so it can come out. And when I add solder here, it'll all be connected. I think this is probably the most stable, well-connected way that I can do this. And because these fuses are somewhat flat, they don't stick out much further than anything else on the board. And behind this board is kind of a large amount of air and space, so it is okay to have things sticking out on this side of the board. On the other side of the board, all right, we have tested this MOSFET. It seems to test just fine. So it is in place. It is now soldered onto the board. It seems to be stable. That is fine. There was a triac that is here. I have ordered a replacement for it. My tester can't quite define what it is. There's a 76 ohm short between two of the pins. This varistor is a new replacement. It had failed. The old one had gotten a varistor. If you're not certain, if you're not aware, is like a fuse, except that a fuse will explode when it has too many amps. A varistor will explode when it has too much voltage. So going from 120 volts to 240 volts is certainly enough to make it explode. The way it does that is it normally tries to shunt all power to a different place. Like it all of a sudden allows connectivity and tries to let all amps flow to a ground source and save the rest of the board. In this case, that is not what it did. It did explode, and power still flooded the board, causing catastrophic failure in many of the other components. Um, Most of the other things on this side have tested okay. All the capacitors that are electrolytic capacitors are generally testing like they are within spec. The only other thing that had failed on the board that I can identify easily is this diode D6, which is right here. I happen to have one of these, and it seemed to test like a short between both sides. Other than that, I've tested almost all of the different diodes and capacitors on the board. As far as I can tell, they are working well. I do suspect that this transistor over here may not be within spec, but it's hard to tell without really finding the model number on it and being able to pull out the data sheet. Um, but at this point, I think I've gone about as far as I can go with replacing the hardware until I get the new triac. And look here, it has arrived. one new triac. Just want to show the comparison when I test the new one. The new triac tests as a triac. The old triac tests as a resistor. So it is definitely bad. It's important not to forget the thermal paste on this. This particular triac could have hundreds of volts going through it. It can get rather hot. So using the heatsink, using the thermal paste is what's going to keep this thing going strong for years to come. There is a lot of copper on the board where these pins are. There's a lot of other solder. It makes it very challenging to put enough energy into the solder to have it melt onto the board. So I'm using the large iron, the T45, um, and it works really well for this case. It's really a good use case for these big pins and these big pads. It's time to address the 400-pound transistor in the room. This little device here, I'm not certain what it is. I want to get closer and take a look at it. And sometimes if you can't read anything, there's a W on it. Sometimes you can't read anything, a little bit of isopropyl alcohol will kind of bring out the label. Gonna give that a try. And as it dries, so I don't know if this is scraped off or if there's something on the chip. Let me see. Oh, yeah, there's some glue or something. All right, this is W2A44. Okay, so I have one of these. They are very commonly used as like an AC transistor. They are the PMBT 3906. Lots of different people have them. They usually just have a 2A with something else or nothing else on them. They are basically 39 volts or 40 volts for the two pins on the bottom. The top pin, which is the collector, is basically 6 volts. So as long as the chip is given 6 volts on the top, it'll allow 40 volts to go through. So it often uses like an amplifier. Um, so I'm just going to test this particular chip to see if it's good. And I have another one you can see right here. So if it is bad, I will be able to swap it out. All right, we're going to start with the black probe, bottom left, pin number 1. Let's just check continuity. This is kilo ohms. It's quite a bit. Kilo ohms is here, so there's no short. No dead short. All right, I'm going to move this into into diode mode, and I'll test again. That's a voltage drop of about 6.6 volts, which is exactly what this should do. Let me test to the collector. Yep, 6 volts, or zero point 0.6 volts. Excuse me. That's exactly what it should do. Ooh, but reversed polarity. This should be an open circuit, not 1 volt. Hmm. So it looks like I'm gonna have to put this other one onto the board. What I basically did is I used my J-tip to kind of pry up the top pin pad, uh, and then I used kind of on the flat side of it to do the other two sides. And what I want to do now is just add a little flux, and then um, we'll add just a touch of solder to the top pad again. Top pad looks a little rough. I suspect that when this transistor failed, it kind of messed up this pad a little bit, but it looks like it'll still work. So hoping that'll be the case. Okay. That side was pretty easy. I'm just going to add a touch to the second side. The reason I'm doing it with a soldering iron and not hot air is I feel like it'll be a little bit more gentle to the component and a little bit more gentle to the board. In theory, the flux I'm using is supposed to be no clean flux, which means that although it can still leave a mess on the board, it shouldn't need to be cleaned off. It won't corrode anything. There's some confusion around what no clean flux is. It doesn't mean that it doesn't leave a mess. It doesn't mean that it's not sticky. It doesn't mean it doesn't look ugly or burnt. It just means that even that stuff shouldn't corrode the metal that's already on the board. So in essence, you still have to clean it off. Here's my take on repairing things of this kind of commercial electronics type. Varistors explode, fuses explode. They just seem to do nothing to protect anything else on the board. My understanding is that they're trying to protect the house more than the piece of electronics. It's definitely clear that they're not trying to protect the electronics. That is wonderful for a hobbyist. A professional electronics repair person would never be able to fix this, at least not in a cost-effective way. But for a hobbyist, it's 1,001 parts that need to be tested and repaired, and it's like a dream come true. So really appreciate being able to fix things like this. We have power. Looks like it works. All right. Thank you for watching.